The theme of our report is sustainable performance of alkali-activated blast furnace cement concrete with high freeze-thaw resistance. The work was done by a group consisting of Professor Krivenko Pavel, Professor Rudenko Igor, Senior Lecturer Konstantynovskyi Oleksandr, and postgraduate student Razsamakin Andrii. To injure the durability of constructions is one more current world tendency of sustainable development of mankind. The most important properties of concrete for a specified case are used for evaluation of durability dependent on destination and environment. Resistance of concrete to freeze-thaw cycles is one of the criteria. The cements obtained due to alkali activation of blast furnace cements for the alkali-activated blast furnace cements are the most prospective ones to ensure advanced service life of concrete structures of special purpose. The peculiarities of porous structure cause advanced freeze-thaw resistance of alkali-activated blast furnace cement concrete. Porous structure of such concrete in one's turn is caused by technological factors such as consistency of fresh concrete, aggregate state of alkaline component, curing condition, and application of chemical admixtures. The modern requirements to consistency of fresh concretes are governed by practice. Production of alkali-activated blast furnace cements, namely under all-in-one technology, causes this expendency of alkaline component exactly in dry form. Thus, the aim of this research was to investigate the effects of technological factors on porous structures of alkali-activated blast furnace cement concrete of special purpose to provide its high freeze-thaw resistance as criterion of sustainable performance. The main constituents of the blast furnace cement type CEM3C were presented by brown granulated blast furnace slag and Portland cement type CEM1 42.5R. The blast furnace cement was composed of 95% of slag and 5% of Portland cement by mass. The alkaline component was introduced in a concrete mixer in dry form or in liquid form in such a way that its content in the concrete would be equivalent. A river silica sand and a granite gravel were used as coarse aggregates. Alkali-activated blast furnace cement concrete was modified by complex admixtures. Complex admixture was presented by sodium lignosulfonate and waterproofing agent based on ethyl hydroxyloxane polymer. Freeze-thaw resistance of alkali-activated blast furnace cement concrete was studied according to the third accelerated test method prescribed by the national standard of Ukraine. According to this accelerated method, the concrete cubes were saturated with a 5% solution of sodium chloride at temperature 18 degrees, and after that were subjected to freezing at temperature minus 50 degrees. Thawing was done in a 5% solution of sodium chloride. A class of concrete in freeze-thaw resistance was designated as a number of alternate freezing and thawing at which a mean compressive strength decreased by no more than 5%. The freeze-thaw resistance of concrete was assessed by the correspondence between permissible number of freezing thawing cycles by the mentioned method and by the first basic method prescribed in mentioned standard. Alkali-activated blast furnace cement concrete was prepared by one-part technology when alkaline component was introduced in a concrete mixer in dry form, and two-part technology when alkaline component was introduced in liquid form. The specimens hardened in water under normal conditions and under steam curing. It was revealed that consistency of fresh concrete is an important factor of porous structure. Thus, increasing of consistency from class S1 up to class S4, while application of alkaline component in dry form, as well as in liquid form, injured increasing of volume of open pores and decreasing volume of conditionally closed pores. Less volume of conditionally closed pores determine formation of minor dense and more permeable structure, which cause deterioration on physical and mechanical properties of alkali-activated blast furnace cement concrete, including freeze-thaw resistance decrease. Application of alkaline component in dry form, in contrast to liquid form, injured high volume of open capillary pores and at consistency classes S1 and S4 agreeably, lack in filling intensity of porous space by hydrosilicate gel caused with this phenomenon. Decrease in volume of conditionally closed pores occurred. Specified changes in porous structure injured decreasing tendency in freeze-thaw resistance. Normal curing conditions of alkali-activated blast furnace cement concrete was more advisable if compared with curing in water or under steam curing in the view of formation of effective porous structure. Porous structure of alkali-activated blast furnace cement concrete at consistency of class S4 and after hardening during 28 days under normal conditions were characterized by decreased volume of open capillary pores as well as by increased volume of conditionally closed pores compared with analogs under water or steam curing. Specified changes in porous structure contributed to formation of alkali-activated blast furnace cement concrete with more dense structure. This phenomenon provided advanced freeze-thaw resistance in contrast to analogs. Application of air entraining and plasticizing admixtures injure higher volume of conditionally closed pores and lesser volume of open capillary pores, which increases freeze-thaw resistance when alkaline component was applied in dry as well as in liquid form. The ways to injure high freeze-thaw resistance of concrete of special purpose were pointed: limitation of consistency of fresh concrete, application of alkaline component in liquid form in contrast to dry form, application of air entraining and plasticizing admixtures, and hardening under appropriate temperature humidity conditions injure closed porosity between 3 and 6% and advanced freeze-thaw resistance. Thank you for your attention.